So, welcome all. Let's wait 5 to 6 minutes for someone to join, and then we shall start our 11th. Uh, I think it's the 12th one. Let me check. This is the 12th session, I think, and then we'll have an extra session on tomorrow. That's the understanding I have with the course coordinators. Let me just check. Yeah, so we have done week 11. Let's do week 12 and then another final session tomorrow on week 13th. So, yeah, let's get going today. Just let's see if someone joins in next 2 to 3 minutes and then we'll continue. Let me have some water till then. Okay, so let's get going. I think today not a lot of people will join. Usually the attendance is one. Yeah, let's see. So Apurva is here. Uh, Good evening, Apur. Hi.
Yes, sir, good evening. Hi, sir.
So this is our second last session, right? You have been communicated for a extra session tomorrow Wednesday.
Okay, sir. I have not seen that, sir.
Okay. Yes, let's get started. I'm sharing my screen, I think. So welcome to the 11th, 12th session. Basically, I'm going to look at physics informed neural network. So what can we expect from the rest of the two sessions that remains? Let's discuss that first. Or before that, Apoorv, any questions or something you have in mind?
No, sir, not as such.
Okay. So what has Sir discussed in his 1 week of on neural networks?
Sir, like he started off with basic machine learning concepts, regression, and all. Then he went on to neural networks, perceptron, different these things. RELU, then sigmoid function, all that. Activation functions,
Okay. And
all
then
that.
did he apply anything to some problem?
Yeah, there was one example, but very basic in nature. Not, nothing related to physics informed PIN and some anything like that.
What was the example if you can just
One minute.
elaborate?
Meaning to say, like he was using like different combinations of yeah, this thing only.
Okay, so
He was just playing
classification,
with the
huh?
data. Yeah, yeah, yes, sir. Classification.
What has he used? It's very nice, that TensorFlow playground. Okay. Nice. Okay, so I believe you are aware of perceptron and other things.
Yes, sir.
Okay. Okay, so this is like just okay, so
I
nice.
think we are doing one more course on machine learning. It's from your institute only, but there is no mention of physics in for neural networks. So I
Yeah,
am
it's a
very
very
what is it? How I mean, whatever I learned in machine learning, there was nothing related to physics or anything like science. It was all about data, statistics, all that only.
yeah, because at the core of it, it's all statistics only. As today also, it might you might see a glimpse of that. Any neural network is not like when we say physics informed neural network, what do you expect to what is your imagination as such when we say physics informed neural networks? Let's start with that.
I just searched on Google. I have just found that it at least makes use of the physical, governing equations. At least it makes use of it. But in machine learning, as you know, you might you would already be knowing it. There's no use of that. That's the only distinction I understand as of now.
Okay. So yeah, there is a very nice definition of physics informed neural network. Let me look it up, and it's a very nice paper as well. Maybe I'll share that. It's a very nice way of looking at. Actually, that's the so basically the reason this is not so prevalent is the fact that the literature is being generated as of now today.
Yes.
So
I think
if
in
we look,
CFD. Yes, yes. Sorry for interrupting.
no, go ahead, go ahead.
Yes, I think only uh, it started off like in core engineering CFD application. It is it goes back to only 2019 or 20. I think only back then the first paper came up using PINN and CFD or something like that.
PIL, PINN.
PINN and CFD. I mean the first
Yeah,
paper I think it appeared in 2019 or something. 18,
yeah.
19.
So
Not very
as
old.
you
Very
were,
new.
yeah, as you're correctly pointing it out, it's not that old. The first few, so well, not exactly. So they have cited few papers which date back to as old as 1992. I think there is one paper here itself. Yeah, this one. So a hybrid neural network first principle approach to process modeling. So process modeling is basically what do you say? Dynamical systems modeling. So you might be remember you might have had a course on control system design, and there are like plant models, right? There are these differential equations. There are like linear operators between two input and output. So they basically go like this. So L being a differential operator in Y is somehow related to, or let's say L1. So any linear function, linear system can be represented by this. Suppose Y is your output and X is your input. So basically, any linear system is basically saying that uh, linear operation on input and output is basically much new, but essentially any process can be modeled using a linear differential equation. This is basically a linear differential operator. or a combination of linear differential operators. So now that is what process modeling can be quickly mentioned, and paper are quite could be traced back to very old, but today I'll also maybe briefly discuss why in very recently have these things emerged so well. And um, I'm not sure if you understand, or if a general student of this course would understand why and how does a neural network work. So I'd be sure that sir have explained some things on weights and other things, but at least this fundamental question, I'm not sure if this has been discussed. So the first question I wanted to, like when I started preparing material on it, was the first question I asked was, why should a neural network work? Okay, so by now everyone has an idea of what a neural network is, what AI is, and what ML is. And there is also something called as deep learning. What are neural networks? We don't understand exactly what's going on. And that is where lectures from Sir's video lectures must have come handy in. He introduces the concept of perceptrons and I think feed forward neural networks and so on. Now, there was another thing, another comment which uh, Apoor made. No physics in neural networks or ML. Okay, so which course have you taken in ISC Bangalore? NPTEL course, I believe.
Yes, it's going on. It's the professor is from chemical engineering department.
Do you know the name of the course?
Yes, sir. Machine learning in core engineering discipline by Professor Anand Govindraj. Anand
Oh,
Govind, not Anand. Anand.
okay. Yeah, that will come up. No worry. ISC Bangalore. Engineering core. What did you say? Engineering, huh?
Yes, sir. Core engineering disciplines.
It's an NPTEL course.
Yes, sir, of course.
Hmm. Why does it have to be of course though? Yes.
Should have come by now. I mean, if you want, I
For
can.
core. No, this is the course. I get it.
Yes, sir.
Let's look at it. Yeah, and you saw that there is no engineering as such throughout this course, it seems, right?
Not, no use of physics.
Yeah, because the point is there is no need of physics in neural networks. So that is quite an interesting perspective to look at ML. There is no real engineering or real non-computer science engineering going on. Let's put it that way. So no non-computer science engineering. I'm pretty sure there is a lot of computer science engineering going on there, but definitely no non-computer science engineering. And it's basically data analytics
Yes, sir. Hardcore data analysis.
and probability
Yes, probability, all that.
and what else? Data probability, maybe a little, and machine learning is what? So yeah, basically probability. It's not even data analytics or anything. Stochastics, we can say it's the same thing, but essentially probability, right? Everything just comes up uh, like nicely under one umbrella of probability, right? And the reason behind that is there are certain natural laws uh, which any problem for that matter satisfies. So at this point, I think this would be a nice detour actually to just appreciate the fact that there are certain bigger laws with more abstract laws than what we deal with existing in nature, and it's quite nice to see that they kind of appear in weird ways in different disciplines. So I was reading this paper for preparing this material. Why does deep and cheap learning work so well? So even they were fundamentally asking this question that why should a neural network work? But at some point, this question is a little different from what is being posed here, because essentially I have not explicitly said that a neural what does a neural network do for me to ask what does that will it work or not, because I don't know what does it do. But here the question is a little different. Here, what do they mean by why does deep and cheap learning work so well? So what the author wanted, at least in the starting of the, I didn't go through a lot of it, but in the very starting of this paper, the author wanted to just, what do you say, wanted us to note that suppose there is a classical problem and you have one image that you want to classify. And let's say that image has like 10 million or something pixels. And let's suppose it's a grayscale image. Then essentially what you're trying to say is you have a input of domain of dimension. Basically, the dimension there. What would be the dimension there? If you would note, it would be 256, 10 to the power 256 or something, I think. No, 256. Um, so every grayscale can have 256 values, 0 being white and 256, 0 being black, 256 being 1. So essentially, this will be 10 to the power 6 to the power 256 or something like that. Not sure. Let me check. Um, so 256 to the power 10 to the power 6. Okay. Wait, let me think. So 256. So if each pixel can take one of the 256 values, then there are 256 possible images. Uh, does that make sense? Let me think. Right. So any image will have 10 to the power 6 values, and right. So it makes sense. So this will be 256 to the power 10 to the power 6. Right. Now, again, I'm digressing and I'm losing your attention or interest. Let me just quickly point out what this author wanted to tell. He said that your input is going to be a large dimensional data, and your output is supposed to be uh, a class of, like, it should lie in this domain. Let's say it's a classifier. Let's say our neural network is just going to tell us if the image is of a cat or not. Then essentially, there are this is the possible number of functions or possible number of what do you say, any arbitrary function will lie in this large, there is a large probability that you have a large input, right? And essentially your uh, neural network is able to approximate this large class of functions. There can be a large class of functions that map this value to this in very small, what do you say, it is a, it's not prohibitive, it is able to do it. And so the argument he makes is that this is a kind of an overstatement. Some practical, like some realistic data will not have this much, like it will not be of that dimension. We know that a lot of images, like a lot of images if we look, we complete garbage. If we look at it, right? You know about noise images, right? Noise images. So the images could look like this, and we know that the no, not this. So maybe a grayscale value, yeah. So you can see that there can be images like this in that data in that set, but we know that such images don't exist uh, in real life, in reality. And so it's not that there is a large amount of reduction or some very sophisticated approximation is happening. Indeed, our sample set is very small. Like the assumption, like our method is not will not like so our method will fail, definitely fail for any random image, right? But it would work only for a very small class of images. And because we are interested in only that small class of images, we think that this neural network works. But it will fail, or it is bound to fail when it goes out of that small class. So it's a little convoluted what he was trying to say. I also not properly put it up there. But essentially, what he wanted to point out was that he talks about some important, um, important what do you say, important features in our data, in our physics, or uh, well, let's talk about that part of it. Essentially, that there are certain features which reduce the size of this dimension, or this whatever you would like to call. So basically, let's see what exactly should we call it. So this means that an arbitrary function is defined by a list of 2 to the power this thing probabilities, way more number than. So basically, he's trying to say this is prohibitively large data set, and still we are able to work around it. So that is what is meant. That is what I was trying to also say. And essentially, what he says is that your data set can be reduced by noticing that there are certain large number of features, uh, large number of features in our real data, as well as the class of functions that we are trying to approximate using our neural network. Uh, and that is what he talks about. But in the way in during his paper, he kind of mentions a table where he kind of compares uh, machine learning uh, lingo, or machine learning bread and butter formulas with a physics based formula. So let's look at that table, and quickly you will realize that there are striking resemblance. So he talks about LNP. So when we are discussing neural networks, we talk about the Bayesian algorithm, and then there are these three. We'll talk about this three approaches. So neural networks are designed to give you only probabilities at the core. So remember that. Essentially, we are kind of dealing with probability at the end of it. Okay, we are we are supposed to be dealing with probabilities. The logic, now you might ask that it's not true, that we are not, basically we are not dealing with probabilities. You might ask, a neural network model, once you feed data to a neural network model, you expect a real value, not a probability in a lot of cases. Say a classification, say you put an image and you want whether it is a cat or a dog. Remember that uh, depending on the type of function, depending on the type of machine learning method you have used, it can tell you the probability of it. It can tell you whether it is 60% probable that it's a cat or not, or it can just guess guess the value. And uh, when it's guessing, basically what it is called is you find out the point of maximum probability. So you know that a cat has the highest probability of, like, this image has the higher probability of being a cat. So you just say cat. Okay. So that kind of, so, but essentially we are dealing with probabilities. Now, if I go back, you would note that in machine learning, you deal with the negative logarithmics of probability. Negative because probability is always less than one, and logarithmic so that what's the logic of logarithmic? Well, I don't know. Let me think. Why do we deal with the negative logarithmic of probability? Yeah, because this formula, the Bayesian formula. So have you come across about the Bayesian formula, Apurv?
Yes, yes, I know Bayesian.
Yeah, so it kind of breaks with the logarithmic value, a multiplication breaks into an addition. So that's the logic of using logarithmic functions. Now, what he notes is that LNP is kind of a Hamiltonian. So Hamiltonian is energy in energy in physics. Okay, and so he mentions that machine learning and physics have certain what do you say?
It's an operator, right? It's a mathematical operator, if I'm not
It's a
wrong.
mathematical operator as well as see. So if we look into it, Hamiltonian quantifying the energy of X. So it tells you energy also. So in if I look into Hamiltonian, wait, it's Hamiltonian, right? What is it? Where is that? Just give me a second. Yeah, Hamiltonian. An operator which corresponds to the total energy of the system. So it's an operator. Don't ask me what is an operator in quantum mechanics and how does it correspond to energy and so on. Not very good with this part of it. But essentially, just if it's for not for us to go into the details of it, and this paper was also not supposed to be discussed my way of going through this session. The whole point I was trying to make was you'll be surprised to know that there is some corollary that you can draw between physics and machine learning. At least I was surprised when I looked at it, and there are a lot of there's an entire list of it. Okay, so he goes in. There's a table of it. Physics, machine learning dictionary. He writes it, and to be honest, I'm not that good in both physics or machine learning to appreciate this table, but I could only get that there is some like there is some one-to-one correlation that this author was able to draw. Okay, and then he goes ahead and makes certain interesting comments, which we would be very which one of the comment is something that we can quickly appreciate. So he mentions that there are certain inherent laws going on in the entire world without us explicitly mentioning them. And one of them is locality. Now, what is locality? He says that anything going on with you will mostly be affected by what is going on around your neighborhood. And this is exactly what we have seen in our numerical methods. We know that our differential equation or our governing equation, when written into a difference equation, or let's talk in only in terms of difference equation right now, we know that only the neighboring nodes affect how we evolve over time or over space. It's the entire thing is dependent on our neighborhood. Okay, and so he mentions that at some point. And let me be honest, we are being very vague and very abstract about it. What are we discussing? We don't know. We are talking about something at some point and then jumping to a next point. But this is because a lot of things are abstract and we can't. We that will be the nature of the two sessions that are going to happen now, today and tomorrow. The logic is that we are not very capable of looking into these things in a little like in detail, and we are just looking we are just being these what do you say um, tourists to these concepts. We'll just look at them from a viewpoint of interest. Okay, so one of the assumptions one of the striking law he kind of mentions, it's not, we can't say laws, but it's principle of physics as he says it, that the thing directly affects that things directly affect only what is in the immediate vicinity. Okay, and goes on into say that uh, So when you look into, we know that a lot of our matrices that we were solving, AX equals to B, were sparse, and the reason for sparse matrices were that it's the locality that only affects us. It's not something that will affect us. Something very far will affect us. Okay, and the only point I wanted to make here was that this is something that we don't explicitly mention in our textbooks or in our physics or any engineering textbook, right? Locality is something that is very obvious, but still not like it's not studied or documented as a proper law or something, because it's a little abstract in that sense. And he says that this is the reason. So locality is one of the reason that allows you to reduce this. So this is one of the properties which reduces this size of the domain which you are dealing with, your input domain or input. So input domain does not make sense. It's only the domain. So domain size is reduced because of locality. There are a lot of small, like the like in the class of functions, possible functions that can give you from x to y. There are only a very small percentage of functions which will respect locality. Okay, so we know, and we in a continuous sense, we know that there are locality can be looked at from a viewpoint of continuous functions or differentiable functions or second order differentiable functions, right? We know that is known to us. So maybe locality is related to continuous functions and differentiability. Okay. Then he also mentions this low polynomial order. I will not go into this part. Little This is something that we can't appreciate it as of now. And then there was also symmetry. So we also know that the symmetry also does a lot of simplifications in our problem. So symmetry is also one of the law he mentions that allows you to uh, reduce your task of approximating a solution to some problem. Okay, and that is what he was principally trying to answer when he said that what does deep and cheap learning what does make deep and cheap learning work so well. Okay, now this problem, what I was trying to point out at this point is a little different. Why should a ANN work is something very principle to uh, like, it's very fundamental what makes them work. And so maybe I'll ask you, have some mentioned about universal approximation theorem or anything like that in when
No, sir, I don't remember.
okay. And so essentially what we are trying to head here is universal approximation theorem. See, part of the intent of discussing physics informed neural network is also to first understand what is neural networks. Okay, it would be nice that we could quickly go and look into physics informed neural network, but essentially they are a variant of neural networks, and we should first understand what neural networks are. And we know that neural networks do kind of predictions and some complicated regression. That is what we understand. But are we aware of any reason why a neural network will be able to do any kind of regression? Uh, right? We don't know that, right? This was like the first of the fundamental questions that was answered by uh, AI engineers. Well, let's not call them AI engineers, but uh, people with seminal work in artificial intelligence. These are like, and these were mathematicians. Okay, these are mathematicians. They were trying to note that uh, under what conditions these neural network will work. And you will be surprised. Actually, it's again, if you know about perceptron, you might be curious to know why is a perceptron have this sigmoid function, or this what do you call it? ReLU is what? Linear. ReLU is
And linear. Yeah, rectified.
rectified linear. linear unit. So why do they have this structure? Why not some more familiar structures? Okay, and that is at the core of universal approximation theorem. So yeah, so let's come to that. But one last thing which I want to point out, like one comment which I want to make here with no physics in ML kind of comment, is that the reason ML does not have any physics or anything is it's more general than that. Okay. Maybe you can appreciate for the fact that when you're trying to classify an image, or when you want to know some regression problem, some mathematical problem, you note that there is no physics into it, right? You have some complicated nonlinear function that you want to approximate, and that for that you just need maths, and you don't need any kind of physics at least. So that is why no physics is there. So now why how come and where does physics come into this whole picture? Okay, so that is what we will quickly discuss, and let me show that to you using some images. Okay, I don't have a good or let me show that. What shall I show you? Let me see. So just to give you a teaser, let me open this thing up. This one. Okay, so let's just give you a teaser and let's try to bring in physics. Okay. Now let's look at the simplest neural network or simplest problem, physics problem that we can work with, and that problem, I think, should be the harmonic oscillator. Not for the reason that the code is available for it, but it makes a nice, interesting case to show you why neural network and why physics can, like neural networks can be informed by the physics of the problem. So suppose you know that there is an some oscillator data you have in time, and you want to model the entire oscillator, harmonic oscillator, or let's say this pendulum or something, or maybe a spring mass system. What you would note is, uh, and you have the data is not, uh, you don't have a nice data. You might have a noisy data. There is a lot of air resistance going on and other things. You might not also not have a large set of data, small data set. So what you best you can do, you can start fitting things, right? And the problem with simply going ahead and doing machine learning or other things, or any other regression, maybe other regressions might be able to do equally better things, but in neural networks you could quickly kind of get some uh, maybe so this is so let me uh, take my statement back. So this is suppose the exact solution is something that we know, but the training data we have are only these dots. So what can a neural network do? What do you expect a neural network to do? The neural network will at best be able to reduce the error at the training points, right? We can very well expect that the error to go to zero between two training data points. So in the region where the training data is uh, is populated, we can expect the model to give good accuracies, and we can expect the neural network to simply fail outside that region, and that is essentially what happens there. Now our intent with neural network is to include the physics into it, so that we can also go ahead and approximate the regions where we do not have more data, or maybe somewhere training has not been done, or let's say this is a system which has certain parameters like mass, spring constant, and dampers. What if we want to just figure out the what do you say, governing equation in it, or if we have an idea of the governing equation but we don't know the parameters of it, and we want to find out those parameter values, and given some other parameter values we want to approximate now with the new set of parameters, how will the response look like, or how will the this function look like. There we can appreciate that some knowledge of physics can help us better train our models. That's it. So physics informed neural networks are nothing but basically training our neural networks with more more what do you say, more knowledge, prior information. Okay, these are called prior. So you have some more information, and this is where physics comes in. Physics can allow you, as I was mentioning, to further reduce the data set even smaller. So you can train them faster, or maybe train them more robustly, and you can expect things to not go haywire outside of the places where your approximation is not that. So your training data is not that populated. So there, what you could expect is something like this. If you pitch in your physics into it. So basically, at one point is you're pitching in differential equations, your differential equation into the training of your neural network. And at one last point, let's also look at the definition of physics neural network at this point. So this is a nice definition, I think. This is one of the seminal papers, as I was mentioning, 2017 paper, one of the first paper on physics informed neural networks. So these PINs are trained to solve supervised learning tasks while respecting any given law of physics described by general nonlinear PDEs. Okay. Note that these are supervised learning tasks. You can't expect them to give you the physics unless you know something a priori. What else? Yeah, nothing much. This is the definition. I wanted to just quote it down. And yeah, so that is one thing. Okay, this image, I think most of us would know, but just for a small discussion, Apoorv, do you understand the distinction between artificial intelligence, machine learning, and then deep learning?
This artificial intelligence is able to make its own decision. Machine learning, like the if the data is available, the model is able to learn. And deep learning, what I understand is it makes use of neural network.
Okay.
Am I right?
So partially,
Yes.
maybe you might be not like I can't say, I can't judge because I'm also not that great in these things. But the big understanding is that artificial intelligence encompasses anything which you are looking boom in today, right? Artificial intelligence is the biggest umbrella when people are talking about these neural networks, machine learning algorithm, and all those things. Okay, now that entire thing is artificial intelligence. Maybe even robotics or computer vision will come under the umbrella of artificial intelligence, and there is no machine learning going on. Okay, so suppose you have a camera into your system, and that detects whether someone is sitting in front of the computer or not. Even that is artificial intelligence, because artificial intelligence, the definition of it is not that um, restrictive. It's basically you have some kind of intelligence, and it could be anything, right? Now, machine learning comes in, as you said, that you want to train our model. So training comes in with machine learning, and that is the subset of artificial intelligence. And there are multiple ways of training your system. You can use all kinds of regressions. There are SVGs. There are all kind of frequentist approach, Gaussian approach. Okay. Now, in that subset, if you are looking into neural networks, and specifically deep neural networks, then that is called as deep learning. Now, what are deep neural networks? Let's look at them a little later. Okay. So nice. So that is one thing. Okay. And so then, so yeah. So deep learning is a subset of AI and machine learning that uses multi-layered artificial neural networks. So it directly says it. Basically, you have multi-layered artificial neural networks. When you say deep neural networks, basically you mean multi-layered neural networks. Okay. Now, what are multi-layered neural networks? You might be able to understand, or you might have guessed, but let's look at them a little later. But coming back to my question, why should a neural network work is something more fundamental than we have discussed yet. The reason, or what was, at least let's think about it. People who started research on neural network, I'm pretty sure they didn't know that it would boom like this, right? Today it has boomed like crazy, but someone who had started research on neural networks, it is such an abstract subject and so much mathematics into it, so much research that has gone into this, that I'm pretty sure that the people, starting of it didn't know. And it was quite curious for me to understand why someone would start research in AI. And the reason, and as you could suspect, this was not a research that came out from engineers. Maybe that is why neural networks do not have any physics into it, because it didn't come out from engineers, right? Core engineers, so to say. Basically, the early research work came out from physiology and all those things. And the underlying principle is that if brain is a network of neurons and it is intelligence, maybe intelligence can emerge from connecting simple processing units. So if you have a simpler processing units and if you keep combining them, then you can get some artificial intelligence. Now, just look at this phrase, connecting simpler processing units. You know what CPU is? CPU is computer. CPU is what? Some computer processing unit? No, central processing units. Central processing unit. That's what CPU is called, right? Now here it uses the word, or I've taken a quote like from some paper. Basically, we are saying if we combine a small um, processing unit, and these are not centralized, then that can generate some intelligence. At least that is what a perception is. And you might, and by and you should be um, what do you say? You should be vigilant, or you should be not persuaded by just this simple statement that simply connecting any simple processing units will give you intelligence. That's not true, right? We can't expect that to happen. So although the genesis of ANN worked on a very feeble logic, let's see what actually is the reason why intelligence can emerge from interconnected simple units. And then we know that at the core of it, it is the uh, perceptron that kind of is at the core of neural networks. Okay. Acha, just as a nice exercise, what do you think uh, a single perceptron can do? Acha, do you understand about the weights and back? Have you heard about back propagation in that lecture?
Yes, back propagation is.
Okay, and you totally understand what is going on in a perceptron.
Yes, I have the basic understanding.
Okay, so what do you expect a single perceptron can do? Can we train a neural network, a simple perceptron for some function? What kind of functions can a perceptron deal with?
It depends on the activation function, right?
Say the activation function is the ReLU or something.
Hmm.
Then okay, so I'll ask you this question. Basically, it's not a question. I'm trying to make it one, but it's not a question. So I'll just good uh, you say interesting fact. A perceptron can actually approximate AND operation. It can also approximate a OR operation.
Yes, it can operate gates, different gates.
Yeah, but can it operate as an XOR? The XOR is basically when your input is 0 0 and 0 1 or and 1 1, then it gives you output is 1, otherwise it's 0. So if they are unequal, then you have input is 1, otherwise it is 0. That's what XOR is. And again, this is another paper that I have looked at, another discussion that I have looked at. Turns out that and operation and or operations are something that perceptron can deal with. XOR is not. It is not possible to deal with. Like with perceptron, you can't model an XOR gate. Okay, so and the reason for it is that the input. So there are two inputs here. So basically, what is going on? There are four possible inputs, right? There are four inputs here, right? Now, if you were to plot them on say this plot x and y, if you plot them on this domain, like basically this is what your input domain or domain looks like. This is the points. This is the inputs where your input lies in this space, right? What you will note is for an AND function. Suppose for an AND function, if your answer is 0, your point is red. If your answer is 1, then your point is green. What you will see is for AND, these three are red, and this one is green. Okay. Now for OR, what will happen? These three will be green, and this will be the only red. Okay. For XOR, what happens? For XOR, these two will be green, these and this two will be red, or vice versa. If XOR is maybe the definition I've put in wrongly, otherwise it's one. So if it is 1, 0 or 0, 1, then your output is 1. So in this case, these two will be green, these two will be red. The reason why a perceptron is not able to model as a model an AND gate is because, as you can see in case of AND, these 3 points are linearly separable. So you can separate them out, right? You can separate these 3 points away from this 1, 1 point. And so you can kind of say that anything below this line is 0, anything above this line is 1. In OR, similar thing. Only 1 point is red, this line shifts. So these 2 points comes on the top of this line. So these 3 points become 1, and anything below this line will become red. In case of XOR, you can't draw any line which gives you this output. So you try to draw any line above which your 2 points, the 2 points you have green remains green, and the two other points which are red remains below that line. There is no such line that will exist there. You don't have a line of that sort for the XOR gate.
There's a in this case will have a non-linear boundary. Like we can have a closed curve
Right,
surrounding either the red dots or the green dots.
right. So, and that is why perceptron does not work. And so we can kind of expect, I will not go into details of how, like, now how are we able to, like, how can we model XOR or anything? Basically, a single processing unit is not capable of much, but if we combine them, then there is hope. At least we have read so that then XOR gate is actually you can actually model it. In fact, you can do much more. Okay, that is one thing. Going back to that PPT. Yeah. So, what's next? Okay. So, yeah. Okay, maybe I'll talk about AI winter a little bit. So what happened was this early research, as I was talking, there are, so again, one more thing, perceptron, this perceptron is not like the only perceptron the world has seen. Okay, there were a lot of perceptron architectures people had proposed. They didn't work, and so did this architecture also didn't work. Okay, early perceptrons had linear activation functions. Those functions were not non-linear. Okay, and so this perceptron structure also didn't initially work. And so in the 1970s to 80s, 16s, 80s, the research on AI was kind of discouraged. Like people were disappointed with the results that they were getting. Okay, because perceptron was not able to deal like simple regression, or as I said, XOR kind of thing was not being able to was not being able to model. Okay, so now then people were discouraged, and that period of it is called AI winter. But then someone figured out that if you were to use a non so that is something called as we call it as non-linear. It's not non-linear. Let me see what is it called. Yeah, it's called discriminatory function. Discriminatory functions. Okay. I don't want to go into the details of what a discriminatory function is, but if your function is a discriminatory function, only then your this entire thing will work. Now, what a discriminatory function is you can separate a class of. So as I mentioned, there is a class. There's a class of inputs of like there are inputs of same class. If you can separate the output of similar classes with classes of or with outputs of different class. So basically, if you have a class in the input and you can, so if suppose there are two classes in your input space, you are able to map them into two different classes in your output space. Only then your function is called discriminatory. Okay, so people figured out that this sigmoid function and this rectified linear unit functions kind of do that, and so people were able to uh, bring in this whole picture of it. Okay, and what was the logic? The logic was that multiple layers of these perceptrons. Okay, there will be multiple perceptrons. You keep adding layers into it. There will be certain hidden layers. There will be an output layer, and there will be an input layer. And that essentially will kind of give you something like this. Okay, what will it give you? It will give you an so sigma is an activation function. Uh, there will be weights which you will multiply with your inputs, and there is a bias associated with the perceptron. So this is the output of any perceptron. Okay, and now if you were to make a layer of it, okay, suppose there is a input layer and there is a hidden layer. What you get is you will get some function like this. Okay. Uh, Essentially, what I'm trying to say here is that a single layer of your perceptrons kind of gives you this function like picture. So if you see, there's a function, there's an activation function, the input of, or what do you say, the whatever it feeds on is a weight. It's a linear, what do you call it? A linear combination of your inputs put in an activation function to give you an output. And this is like outputs at one layer becomes the so in input of one layer, what is the output of the of that layer? So basically, let me rephrase it. Suppose you have lth layer, right? Your input to lth layer is x to the power l. So your output to your lth layer will look like something like this. And this, without going into too much derivations, it looks like a function, some functional value, right? Depending on x, your output will be there. So you know that there is a function kind of functional picture that you're getting with these layers, right? This is what we will expect. That's not nothing new. Now, what happened was in 1990s, people actually showed that this functional form can take up any value or can take up any form actually. So that is what universal approximation theorem is. It says that So the theorem says that a neural network with a single hidden layer, if allowed to have sufficiently large perceptrons, can approximate any function, any functional form to any degree of accuracy. Okay. So if I have that there, let me see if I have the universal approximation theorem somewhere. Let's read that. So let sigma be a continuous discriminatory function, the activation function as I mentioned. The finite sums of the form, this is the finite sum of the form, we saw this, are dense with respect to the supremum norm. Okay, so this is the derivation. What does it say? It is dense. Well, again, this is a lot of mathematics going on, but let's see if there is a simpler statement of this theorem. So now let's focus on the actual proof. So we don't want to see the proof. Maybe it is in the top. Let's see. It is a fundamental states that certain type of neural networks can approximate certain functions to any desired degree of accuracy. The theorem suggests that a neural network is capable of learning complex patterns and relationship in data as long as certain conditions are fulfilled. So there are certain conditions to your neural network that requires to be fulfilled, and then you can approximate any universal function. Okay. So and read this line. The universal approximation theorem is the root cause why ANNs are so successful and capable in solving a wide range of problems in machine learning and other fields. What I wanted to point it out to you was our intent to bring in neural networks into our CFD or any physics-based solution. The assurance that a neural network will be able to do it comes from this universal approximation theorem. Okay, that is just I wanted to emphasize, and that essentially that there is such an algorithm that exists there. We don't want to go into the depth of it, the details of it, but just that there is this theorem which says that some function can any function for that matter can be approximated if you have uh, there exists a neural network that can approximate your function to any degree. That is what the statement for universal approximation theorem would say. Uh, why I'm pointing it out to you? Suppose you are trying to train a physics informed neural network, and what you are realizing is that you are not able to train it properly, and your function is not getting approximated well. So you can't say that you can't suppose that neural networks might not work with your particular problem. That is not possible because it is a universal approximator. Neural networks are universal approximators. They will work if you have correctly. If basically it's not that any neural network will work. There exists a neural network that could work with work that could work. And the only problem with this approximation theorem is that nobody tells you how to get that neural network. So that structure or whatever that will allow you to approximate your function nicely. That is something that you don't have a formula for. You don't have a recipe for that. Okay, and that is where you kind of some kind of art comes in, hands-on experience comes in. You're trying to change number of hidden layers, number of uh, hidden variables, number of layers that you would change, learning rates, other details, all kind of stuff that you would change. That is something that will come in that part. So that is the training of your model. Okay, that is something that is the practical problem with your what do you say approach or anything. But essentially, a theorem says that there does exist a neural network that will be very nicely be able to approximate whatever you're trying to regress or like that. So that is, I thought that is something important to first discuss uh, before we go into neural networks. Okay, fine. What else? Okay. So I hope this was a little clear. Okay, one more thing. The fact I kind of mentioned, right? That there is this intent, like there is this not suspicion. There is an anticipation that uh, intelligence can emerge from simple processing units, right? Connecting simple processing units. You see the early research on this is the paper on universal approximation theorem. Okay, this is the paper 90. This is the famous paper which says that uh, neural networks will be in universal approximators. This paper itself mentions that you might remember that in digital systems, like even in our numerical methods, we kind of expect a continuous function to be approximated by small time steps or small piecewise continuous uh, proxies of that regular function. So there's a continuous signal. This is discrete. So something when not this one. So see, uh, like this. This one is fine if it opens up to a nice image. Yeah. See, a continuous function can have a discrete analog, right? It can have a discrete analog. As long as this time step is small enough, in the limit that this time step goes to zero, we know that this will very well approximate this continuous function, right? Now, why I'm bringing this thing up here is that even that early paper mentions that simple small delays. So it mentions that small unit delays and constant multipliers can approximate any continuous function for that matter. And you can kind of think that these observations were kind of motivating the universal approximation theorem, that we kind of expect neural networks to work because we are kind of giving unit delays or any kind of like that sort of things. Okay, so it has the capability of representing any kind of function or any kind of pattern. Any complex pattern can be represented by ANNs. Okay, so still a little wavy and other thing. Like I've not been very precise and very uh, what do you say? Yeah, precise only, but still kind of get a feel for it. Okay, we save this. Skip for it. Close this. Okay. One more thing which I wanted to point out. The reason, as we were discussing just while before in the starting of our course, that we have seen a surge in physics informed neural network very lately. It's very what do you say? Just recent. It's very recent, and the reason for it is in parts some a technique called as automatic differentiation. Okay, so you know that back propagation is something by which you train a neural network, and it was actually until back propagation was what do you say was prepared or was identified as a possible explain like as a possible um, way to train neural networks. The AI was still in winter, so So backpropagation was an important milestone in AI research that allowed us to actually practically train our neural networks. Okay, so it was a mammoth task. Once this representation is fine, you can have a lot of weights. But how do you tune these weights so that it can approximate your data is another big headache, and that is where backpropagation comes in. Uh, and similarly, you also have this automatic differentiation. Okay, and automatic differentiation generally, basically what you would do is you will go to weights where your local differentiation with these weights on your output is zero. So you would want to go to local minimas, and you would do that with stochastic gradient methods and so on. Uh, but what physics neural network do is they kind of employ or exploit the technique of automatic differentiation, and they differentiate it. They do not differentiate it with the weights of your neural network, but with the inputs of it. So if you vary the inputs, how does your output change? And that differentiation kind of thing, that differentiation you bring in because you when you are kind of approximating, or where you're, whenever you are kind of um, forcing your differential equation or governing equation or your physics, your governing equation will be in form of a partial differential equation. So you need different differentials, you need derivatives, and that derivative comes in through the technique of automatic differentiation. So that was also something that was recently figured out. That is why people have now started exploring physics informed neural network, because now it has become easier for us to uh, estimate the differentiations and all those operators into our into our framework, and only then we can use uh, neural network, like we can use neural networks and train them on PDEs and so on. Again, not very clear, but just listen to me. I think, yeah, maybe something gets to you. Okay, I think this is also fine. Let me see it this up. Now we'll go to this. We'll do a hands-on experiment, like hands-on code to it. You have already seen that I have a that we can do a piece of code on physics informed neural network. Let's do that. Okay. Maybe in next session, then we can kind of close this part and then have a small discussion of what, like a overview kind of thing, that whatever we did. Yeah, I think that would be fine. Acha, are you aware of this triangle? Has sir discussed this part of it? That probability gives you, either it can give you prediction, it can give you unsupervised learning, it can give you classification. Are you aware of this fact?
Yes, sir, but sir did not discuss this. I think.
But you know about this because you have taken that course.
Yes.
Okay. Because it is only you that is like who is attending the classes. I might Let's not go into this. It's nice though. It's an interesting thing. Okay, I've saved this part. What else? Gaussian processes, maybe we'll look into. Are you aware of Gaussian processes?
Yes, sir.
Okay. Okay, so now let me set it up. Okay, so let's write the code for the entire thing. Actually, what I was doing was this repository that I had cloned using from GitHub, and I was kind of playing around it, okay, to see what was going on. And to be honest, let me tell you that physics neural network are not very like they are not very attractive if you go into the details of it. Okay, they are not easily trainable. At one point, it is quite hard to train them. So just remember that fact. Okay, it's not that it's some magic that will solve all your problems. So that does not happen. That's it. That is what I wanted to just say. Okay, let me download this. Give me a second. Okay, so simple stuff. What we are going to do is we are going to use PyTorch for our neural network training. Uh, you can quickly go and see how typical neural networks are trained, and kind of we are going to do that only. Okay. So suppose we're going to use some helper libraries also. So let me see. So some basic library inputs that we need to do. Then we are going to save GIFs. Okay, we are going to save, or do we need this? Let me see. Yeah, let's save this. So this is some helper library. For some visualization, we need this function. And then let's look at oscillator. So this is the function that we need to generate data. In real life scenario, you will have your data at hand as a first step. Okay, but for demonstration purpose, we do not have any data or anything for that matter, right? And now, just give me a second. Okay, so as I was saying, so this is what we will use for uh, to generate data. What is it? D, so D is less than whether not. What is this? Okay, so basically, this is some sophisticated way of just generating this data. Okay, uh, D is the K by. So what is D? Let me write this down. D is C by 2M. Okay, and then what else there? D is C by 2M. Then you also have omega naught, or W naught is K by 2M. K by M, sorry. Does not matter for us because at the end of it, it is just this thing is something that we know. Okay, No need to get into, yeah. So basically this is an oscillator. Let's look at how this, how does it generate good data? Okay, let's plot this. Okay, this is something that I have to do. We have some data. Okay, let me, it's 900. Let's take our thing. Let's take this data. Okay, maybe not till, we'll take some data. This will be our training data. Okay, 800 or what is it? 30 I'll do. Yeah, that's fine. This is okay. Now let's train a simple neural network out of it. Before that, we'll first have to construct a model. We'll have to construct this network. Okay, whatever we have seen, this kind of stuff we'll have to construct. That we'll do. So this the name of this thing is called uh, feed forward neural networks, and this is also what is FC and I forgot. The name is fully convolution network. Okay, so we are going to create a fully convoluted network. Okay, and for that we need to actually create a class out of it. So let's do that also. You're with me, right? You're with me. Are there things which you're not able to follow?
No, sir, it's fine up to now.
Okay. So for this entire structure that we need to create, we are going to use torch. Okay, PyTorch. And this is kind of customary that we'll have to do it. Okay, if we want to train using PyTorch, we need to create a class, and the class will decide the structure of it, and it will have certain parameters. So basically, the number of inputs that you have, the number of output that you have, number of hidden layers, number of hidden outputs, sorry, number of hidden variables, and number of layers that you are going to have. Okay, so number of hidden layers in this case will be 3. Uh, Number of inputs here in this case are like 4. Number of outputs are 3 here. Uh, on this, just give me a second. Hello. Sorry, I had received a call. Anyways, one more thing, I will have to kind of stop early today. We'll stop at 7:35. So not uh, maybe 10 more minutes and then we'll stop. Okay. So yeah, so as I was saying, in this layer, the number of hidden variables are like 336. Only in this variable, on this layer, you have like 3 and 5 variables. the way we have dealt with the construction that we'll be subscribing to, we'll have number of hidden layers common. Okay. So this is the FCS. This is the not FCS, FCH. FCS is the fully connected started. Yeah. So basically in the starting, this is the starting layer. Okay. This is the starting layer. We'll keep the activation function is 10 hyperbolic tangent hyperbolic function. And this is like again neural network libraries from PyTorch. So this is something that you have to just simply follow. You can ask ChatGPT to generate a fully convoluted network or anything, but this is like um, straightforward. So you have a sequential layer. This basically this is signifying as the layer activation you're giving. Then you will have a hidden layer, hidden set of layers. So and you see n inputs. So you this is signifying n inputs, then n hidden layer. So inputs are n inputs, and the outputs will be n hidden. Again, FCH will have n hidden layers and n hidden inputs, and then n hidden outputs. And this you do for n number of times. Okay, n layer number of times, and then finally you get the output of it. So I start hidden and then exit or end. Okay, three set of things. I might have gone quickly over it, but this is customary, not want to spend too much time. Okay, this part of it, let's keep it as black box. Nothing very special about it. Then then what's next? Okay. Okay, and one more visualization function that we will need is this plot results. Again, let's forget about this plot results. Okay. Let's look at how a neural network, simple neural network, trains over this data, training data. Okay, let's look at it. Train it over 100 point. Okay, so let's look at what is going on in this piece of code. First of all, because you're going to run the same, so basically this is again a customary step that we need to do. Our neural network is basically a lot of initial weights that we take. That is, the solution is dependent on that. And in general, that will be a little randomness will be there. But to remove that randomness, we do this, take a customary step. We manually seed something. And just let's not go into what is going on there. This is a customary steps. Let's take it. Okay. And now we define a fully. So earlier we had defined a structure of it. Now we are defining an object out of it. Okay. So we are taking one input, one output. Okay. So this, because we have one input, right? The time is the one input and output is y. So this is a simple signal regression that we are doing. We are basically regress, want to find how we want to find f of x, y of t, right? We want to find y of t. Each layer will have 128 number of variables, and there will be three layers. Okay, this is the model. Now we will require a optimize back propagation stuff also. So basically now we need to tune the weights, right? We need to tune the weights of this fully convoluted network. For that we need an optimizer, and we are using Adams optimizer. I'm not sure if you've heard of it.
Yes, I heard of it.
Yeah, adaptive adaptive moment estimation. Okay, it's not a name of a scientist, it's an acronym, just an acronym. So you do this at this level of training, have you done before? just using this.
No, I'm not. At least I know the theory part.
Okay, so at least this code you can just quickly generate and see what goes on. So every time you do this for 100 times, right? So 1,000 times you keep tuning the weights. Every turn, you first of all you define zero gradient. So this is again a customary step. You need to remove earlier information stored in your optimizer or in your backpropagation step. You need to remove all the gradients that are associated with your um, basically in the step of a back propagation you need to remove some gradient, so that is what this line does. And now you define the error that you want to minimize. Okay, so first of all you figure out what output this your model gives, your nascent model will give. You write the loss function will be the error between the actual data, your training data, and your output, your prediction, and you take a mean square average of it, and then you back propagate. This is the back propagation step. Okay, you back propagate and you take a step over your optimizer. So you tune your parameters. This is the way you write. You train a neural network in your PyTorch. Okay, in every step, we do basically we want for 1,000 steps. Let's look at how the solution evolves over 1,000 steps. Okay, what you'll see is initially it was some near zero value, and quickly it starts to take these values, right? This is the 1,000 step kind of thing. This is what happens. Let's quickly see what happens in 5,000 steps. Okay, next 1,000 step. What happens in the next 1,000 steps? Let's look at 5,000 steps. Let's look at that. I'll remove this part. Okay. So I've continued from this earlier step only. Now you'll see further fine tuning will keep on happening. Every 100 step, you will see you will get closer to your actual solution. We'll stop at this point. We'll continue from this. Okay, next time, basically tomorrow.
Okay, sir.
Okay, let's just stop at once this stops. Let's stop there. What essentially you're seeing is slowly and slowly this neural network will start predicting exactly how your data is. Basically, it will minimize the error. That is what it is doing, right? But this will happen over several training steps and so on. So this is where we'll stop. Now, what is the issue with this kind of approach? There's nothing wrong with this approach, right? If we train it well, I think we'll get exact matching. I wanted to kind of see that, but let's stop here. Let's continue tomorrow. Let's continue tomorrow. Okay. Let's stop here. It is taking a lot of time. But I'll leave you with some questions. What is the drawback with this? Have we induced any physics into it? Is there any point of inducing any physics into this? And how will we do that? So these are some similar questions that we can look into. Okay. What you are seeing is slowly and slowly it is kind of uh, meeting the actual output from. If I just stop and generate this thing, GIF, you can actually see how it evolves. Okay, you can see that. Taking time. see how it is slowly and slowly approaching your true solution. So, okay, let's discuss this part. So this essentially you'll see over some time, this will start behaving exactly like the actual solution. Okay, that is something that will happen. So I'll stop here. We will continue with this code tomorrow. Right. So let's meet tomorrow. Okay.
Okay, sir.
Yeah.